Hello everyone, and welcome back to our class in Artificial Intelligence and Machine Learning in Finance. Now in this video I want to talk a little bit about some additional details of the multiple linear regression model. In the last video we've already talked a little bit about how to assess the model fit. We've seen that in contrast to the regular R-squared, we should use the adjusted R-squared because actually when including more and more predictors, when including more variables in our regression model, the R-squared can actually only go up. It can only increase, it will never decrease, so that at some point we'll include unnecessary predictors, predictors that are irrelevant, and actually this will reduce the model fit in the sense that we get overfitting. We have a better fit on paper, but actually we're including unnecessary complexity in our model. So that's why in the adjusted R-squared, we take the R-squared and we correct the R-squared by the number of variables we've included. So actually adding noise variables to an already well-fitted model will decrease the RSS only by a little bit. So the adjusted R-squared punishes the model for every included unnecessary predictor, every noise variable that is included in our model. So to see this, okay, so in this slide we can see that for the credit data, actually the adjusted R-squared increases to some point, and including more and more predictors doesn't really change the adjusted R-squared. So actually here for I think this is 7. Yes, this is 7. For 7 predictors, we get an optimal point where the adjusted R-squared doesn't change too much. Actually, we could have already stopped here, maybe with 4 or even 5 predictors. And including additional predictors doesn't help us in explaining the variation in our response variable. So this is important now. In multiple linear regressions, use the adjusted R-squared rather than the R-squared. Okay. Now, after having fitted our model and after having estimated the coefficients beta 1, beta 0, beta 2, etc., we want to predict values. We want to forecast. Now, how to do this? Very simple. We take equation 15, which said that we can take the coefficient estimates, we can enter the values for x1, x2, x3, and so on. And then we get a prediction, a forecasted value for y hat. And this is what we will do. You take the estimated coefficients, beta hat 0, beta hat 1, and so on, and you include values for your predictors. Can be actual data, but you can also make sort of a simulation. And then if you compute equation 15, then you get your estimate, your predicted value, your forecast for the response variable. Now remember that obviously the forecast will include a bias, and this bias will stem from 3 sources. First of all, we have imprecise estimates of beta 0, beta 1, beta 2, etc. So even with using OLS, even with using ordinary least squares, we will have some imprecision in the estimation of our coefficients because we don't have infinite data. We only have a sample size of, let's say, 1,000, 5,000, even 100,000 observations. This means that there is still some estimation error that will include or induce a bias in our forecast y hat. Second of all, the assumption underlying all of this is that we are using a linear regression function instead of the true function f. Now, in the population, there seems to be, or no, that doesn't seem to be, but there is a relation between x and y, between our predictors or the predictor variable and our response variable y. And this relation is the function f. In our modeling approach, we've assumed that f is a linear function, that we can use a linear regression model. Now, this induces model bias. Might be that f is actually nonlinear. If that is the case, obviously we'll have a bias that stems from the fact that we've chosen the wrong model. And last but not least, our third assumption here is that we don't have a clear relation in the sense that y is with 100% a clear function, linear or nonlinear of f, but our assumption is that y, the response variable is a function in our predictors, and we have still some random noise. That's the error term. We have made some assumptions on the error term, for example, that it has an expectation of 0, it has constant variance, but we still have the error term. So even if our model is correct, if it's a linear function, even if we've estimated the coefficients perfectly, there is still some irreducible error that stems from the fact that some noise will always be in the data, and that's the error term. So never expect your predicted values to be 100% perfect, because we have 3 sources of errors, 3 sources of biases in our predicted values. Okay. Now, how can we extend the multiple linear regression model? The first extension is qualitative predictors, our qualitative predictors. Now, in the examples before, we've already seen some of them, but most of the time we have metric variables, quantitative variables. For example, could be income, could be a price for a stock, etc. But some variables are actually qualitative. For example, age, gender in our credit card data. So how should we deal with qualitative predictors? If the predictor is a qualitative variable, it's pretty simple. We can use a dummy variable. For example, if we want to code gender in a very simple way, we can also include more gender types, but if we only use 2, female, male, it's xi equal to 1 if the ith person is female and 0 otherwise. And then we get a dummy variable for a predictor with only 2 levels, and we can include it in our regression just as any quantitative model variable. If we have k levels, we can actually code this in the following way. We only use k minus 1 dummy variables. For example, if we want to code, let's say, age in a very simple fashion, we can say, we can say dummy variable x1 is 1 for age smaller than, let's say, 20 years. And 0 otherwise. x2 is 1 for age larger than 20 years and smaller than 40 years, and then 0 otherwise. And if, for example, we only have 3 levels, then we need 2 dummy variables. So if both of these are 0, it's clear that actually in this case the person is older than 40 years. So we have x1 for the young people, x2 for the people between 20 and 40. And if both are 0, it's clear that the person is older than 60 years. And we can do this on and on. For example, x3, for example, 1 for age, let's say 40, age and between 60. And then it's clear if all 3 dummy variables are 0, it's a person that is older than 60 years. So this is the way how to code qualitative predictors, but you need to be careful when interpreting the estimated coefficients. Now, if you have an estimated beta coefficient for, let's say, a metric variable, it's clear that you can interpret these coefficients as a, for example, a 1% change in the predictor leads to a beta % change in the response variable. Now here, it's clear that you have to interpret the coefficient as a switch from 0 to 1. So what happens if you no longer have a male observation but a female observation? Then this is the interpretation of the coefficient. Okay. Now this is a qualitative predictor. How can we extend the multiple linear regression model even further? By including so-called interaction terms. For example, imagine predictor xi increases or decreases the effect of a different predictor x2 on our response. To measure this synergy effect, as it's called in marketing, we can use a so-called interaction term. So we set up our regression model. Response equals intercept plus slope 1 times x1 plus slope 2 times x2 plus a coefficient, that's the interaction term beta 3, times the product of x1 and x2. This is how you can do it with an interaction term. Again, be careful when interpreting the coefficients beta 1, beta 2, and beta 3. Beta 3 is the interaction term. It means that it measures the effect of x1 on y if x2 changes. The coefficients beta 1 and beta 2 now also measure something different. Actually, it's now for even more important when you're using qualitative predictors. Beta 1 measures the effect of x1 when beta 2 is, actually no, x2 is 0. So this is the isolated effect of x1 if x2 is 0, and beta 2 measures the effect of x2 on y if x1 is 0. So this is a little bit tricky, and also to correctly measure the interaction term, one must include x1 and x2 in the regression as well. So this equation here is correct in the sense that we have included x1, x2, and their product. This is particularly interesting when you have an interaction between a qualitative and a quantitative predictor. For example, imagine x1 is income and x2 is gender, male, female. In this case, the interaction term beta 3 would measure the effect of gender on income, on say health, if the response is health. So how much does gender affect the effect of income on health? Quite interesting. And beta 1 and beta 2 would be the isolated effects, for example, for male and female. That's quite interesting when you combine a qualitative and a quantitative predictor. What else to do? Now we've seen we are talking about a linear model. What to do if, for example, we see that the effect of x on y is probably a nonlinear one? Well, you can use a polynomial regression. Let's say predictor x1 influences y nonlinearly. We can use a polynomial regression. That is, we include x1 and the squared values of x1, so x1 squared. Now, see that including nonlinear terms, such as x1 squared, does not change the fact that this is still a linear model. It's still linear in the sense that we have the intercept plus x1 plus x2. We could have also written x1 as, let's say, x2 or x3. We could have redefined our variable. We don't need to know that this is actually a nonlinear term of x1. So it's still a linear model. We can use OLS. It doesn't change anything, but it can lead to a better fit. And actually, using higher polynomials can lead to such a good fit that, again, as was the case with unnecessary noise variables, we get the problem of overfitting. So this is a problem, but otherwise, if we suspect a nonlinear influence, we can try polynomial regression. Let's look at this in R. First of all, load the library ISLR, and the linear model is quite simple. We use the car, the auto data, so we are trying to explain mileage per gallon, so how many miles you can get out of 1 gallon of gasoline, and we are explaining this with horsepower plus the squared value of horsepower, and see that, let me highlight this for you. Actually, where's my mark? This is strange. Here, here's the one. You need to use the function I. You cannot simply include horsepower hat 2 because actually the hat is a different function in R, so you need to use this function I here. Not very nice highlighting, by the way. And you can see that this is a model y equals x plus x squared. And this is the call. These are the results. You can see the residuals here. And then these are the coefficient estimates. The coefficient estimates here clearly show that the squared variable of horsepower, the polynomial term here, is also highly statistically significant in our regression. So actually, if you were only to include horsepower and then estimate a second model with horsepower and its squared values as a second predictor, you would also see that the multiple and adjusted R squared increase considerably. So yes, it seems as if horsepower and a polynomial term are needed to better explain the mileage per gallon response variable. Okay. Now, in this plot, you can see three different models. You can see the linear OLS fit and the linear model. You can see a polynomial regression using second degree polynomial, and also a polynomial term of degree 5. Now, as I said, it is often the case that there might be a nonlinear effect between predictor and response variable. However, including more and more polynomial terms in this regression will ultimately lead to overfitting. And this can be seen with the green line. Actually, you can see that such a line like the blue line is fully sufficient to explain the data. You don't need something that is wiggly like the green one. So actually, including horsepower squared is sufficient to explain the data. You don't need a polynomial term of degree 5. So overfitting is the case here with the green line, but also the linear model underfits the data, which is quite clear. So it's okay, but a polynomial regression is much, much better suited and gets a better fit. Now, what else can happen in multiple linear regressions? Actually, there are a couple of problems that I only want to shortly comment on. The first one is nonlinearity of the response predictor relationship. So we have a nonlinear relation between x and y. We've seen this. One can use residual plots to identify this problem and then, for example, use a polynomial regression or more sophisticated models. The second problem is a likely correlation of error terms. Now, the idea and the assumption in the OLS model is that the error terms are uncorrelated. If they are correlated, we have a problem. Our model assumptions are no longer true, and we can only use good causal inference and good experimental design, if we have experimental data, to counter this, because usually a correlation of error terms stems from the fact that we have omitted variable bias, we've missed out one important predictor, we have reverse causality. It's not x that is driving y, but actually y is also driving x, so we have reverse causality, as we call it. And all of these problems, omitted variable bias, reverse causality, they lead to a correlation of error terms because the error terms are picking up something that should have been included, and then we have a problem in our estimation. And we use causal inference to tackle this problem. We are likely not talking about this in this lecture, but this is a huge problem in empirical analysis. The third problem is a non-constant variance of error terms. One assumption is homoscedasticity, meaning that the error terms have a constant variance. If it is not constant, for example, we have an increasing variance with more and more observations, one central assumption of the OLS model is violated, and we can use, for example, weighted least squares. Then we have outliers and high leverage points. Outliers meaning extremal values of our response variable, and high leverage points being extremal values of one predictor variable. What we can do is we can try to detect these outliers and high leverage points, and then, for example, use Winsorization or simply exclude these data points from our analysis with all problems that are attached to these methods. And last but not least, we have colinearity, multi-colinearity, meaning that x1 and x2, for example, share a high correlation, and this means that one of the variables is obsolete. You don't need x1 and x2. The information that is needed to explain our response variable is already included in x1, for example. Then we can exclude x2, we can drop it, or we can orthogonalize this collinear predictor. And how can we decide whether we have collinearity? We can use the so-called variance inflation factor. And I'll get to these in just a bit. So let's start with the nonlinearity of the response predictor relationship. We can look at the residual plots. For example, here, if we use a polynomial fitting, left, it's a linear fit. Right, it's the quadratic fit with the polynomial regression. And as you can see, the fitted values in the residuals should actually look rather like this. In this case, we would say, okay, there's no clear trend. It's around 0, and we don't see that for very small or very large fitted values, we have a certain trend in the residuals. Now, with the linear fit, we can see the red line, that's the mean fit. You can see actually, yes, there is a trend. It starts out very high, goes back to 0, and then starts again. So this is an indication of a nonlinear relation. And if we do the same for the residual plot, we can see it's almost constant, and this is how it should be. So from the residual plot of the polynomial regression, we can see that, yes, it seems to be as if the relation is nonlinear, and a quadratic model is much better suited than a linear one. Now, let's go to the second problem we have, which is the correlation of the error terms. Now, I told you that this usually stems from biases like omitted variable bias, reverse causality, and we cannot do too much about this without using more sophisticated models for causal inference. However, how can we decide whether we have such a problem here? And to see this, this is a plot. These are 3 plots where we have simulated data with different correlations between adjacent points and adjacent residuals. Now, if we simulate data and our assumption of uncorrelated error terms is fulfilled, we have a correlation of 0, then you can see that we have a residual here, the next one can be here, can also be down. So there is no clear trend that, for example, this observation leads to another observation, another residual being here or here. Now, if we increase the correlation between the error terms to 50% or even 90%, you can see that we have trends, and it looks like a time series, and this is a problem. Now, here you can see it's highly likely that when you have a negative residual, the next one will also be negative. And this is due to the fact that the error terms, by construction in this case, are highly positively correlated. So this is how you can try to decide whether this is a violation of our assumption. Again, use a residual plot. Now, the third one is non-constant variance of error terms. Here you can see one example where you have the fitted values and the residuals, and actually if you only plot the mean of the residuals, you would say, well, there's no trend. However, the dispersion, the variance of the error terms increases dramatically with the data. And this is what you can see from this funnel shape of the residuals, in contrast to the one you see on the right. Now, in the left picture, in the left plot, we clearly have the problem of heteroscedasticity. The variance of our residuals of the error term in the data increases from left to right. But one simple remedy for this is to use the log of our response. And actually, if we do this simple transformation, you can see it almost looks like the variance stays the same over our full sample. So very simple remedy, might not be as simple as this, but this is again how we can decide whether heteroscedasticity seems to be a problem. Next, we have outliers. Now, outliers are extreme values of y. For example, this observation here, number 20, as you can see, this is an outlier. Now, with the outliers, the problem is that actually, if we have a look at the next plot, actually here, sorry, with the red line and the blue line, those are the linear fits for the data with and without this outlier. And as you can see, the blue line in which we fitted a linear model to the data and we've excluded the outlier doesn't change too much. So actually the outlier for this response value doesn't really change our linear model. It doesn't change the linear regression line that we are fitting. However, the problem is that including the outlier can lead to other problems. For example, it will lead to an increase in the residual standard error, so the RSE will increase, and actually the adjusted and R squared will decrease when we include the outlier. So the model fit is getting worse. So we could think about excluding this outlier. You can also identify this outlier by looking at the residuals in the middle plot here. Again, 20 is far away from the remaining residuals. And if we studentize the residual, that is, we take it and divide it by its standard deviation, again, still it's an outlier. So yes, one could think about excluding this outlier. Same thing for the high leverage point, which is number 41 here, observation 41. And this is an extremal value for x, for a predictor. Again, you can see that actually if you plot x1 and x2 against each other, this is a high leverage point. Now with high leverage points, it might be, actually you can see this here, that the regression line, it changes. Actually in this case not too dramatically, but yes, it does change, and this is a problem for high leverage point. That's why it's also called high leverage points. One single observation can affect the estimation of our regression line, or the regression model and the coefficients dramatically. So actually the coefficient estimates are heavily affected by high leverage points. And again, one could think about excluding this observation. And for this, we can also estimate the so-called leverage. And you can see observation 41 has a high leverage in contrast to the outlier observation number 20. Last but not least, colinearity. Colinearity meaning that x1 and x2, for example, are strongly correlated with each other. And here we are using the credit card data, and this is limit and age. And as you can see, those two variables are not really strongly correlated with each other. It's different with limit and rating. As you can see, there's a strong linear relation between the two, and including limit and rating in a regression model will lead to problems. Why? Because if you remember the estimation of the coefficients in the multiple linear regression case, you remember that the coefficient estimates are given by actually the matrix X transpose times X, and then you have to invert X transpose of X times X, and you will get numerical problems. Now, if two variables are strongly correlated with each other, you can imagine that in linear algebra, these two variables form two columns of our matrix X. And if these two are almost linearly dependent, the information is obsolete of one column. You can leave out one column. If you're not doing this, in this case, you shouldn't. The problem is that inverting this matrix becomes numerically unstable. And this is what will happen. So the coefficient estimates are actually strongly affected by this, because you now get two numerical problems. And this is shown here. If, for example, you have beta limit and beta h, those two from this plot here, we saw that those two variables, those two predictors, are not collinear. And actually, it's quite easy to find the OLS optimum, which is here. So these contour plots are the ones for the RSS. So we are actually, again, if you remember this, we are minimizing the RSS. So actually you can see that it's quite simple. If you, for example, as in the optimization algorithm, if you start out here, it's quite simple to find this point, because this is actually the point where the RSS becomes minimal. Now, this is the same plot for limit and rating. And as you can see, the contour plots become quite nasty. And it's now much more difficult to find the OLS estimate of these two coefficients. Why? Because the function, the RSS function that needs to be minimized, looks rather, how should I put it? This is not as nice to optimize as, for example, this left plot. So it's a numerical problem, colinearity or multi-colinearity, what should you do? Well, you can simply leave out limit or rating. The information is already included in the other variable. You can decide on this using the so-called variance inflation factor, and then you can also orthogonalize this. So you regress x1 on x2 and you use the residual. So you're only using the information in x2, for example, that is not already in x1. That's one possibility as well. So this is colinearity. And this is all I wanted to talk about in the section on multiple linear regression. And in the next chapter, we'll look at penalized linear regression models, especially Lasso and ridge regression.